Hello, my name is Christoph Langhammer, and I will present for you today the history of plasmonic hydrogen sensors. To start with, I would like to give you some background about myself. So I'm originally from Zurich in Switzerland and have a master from ETH, and moved to Sweden to do my PhD at Chalmers University in Gothenburg, which I finished in 2009. And about at that time, I also co-founded Insplorion AB, in part based on the work of my PhD. These days, I'm professor of chemical physics at the Department of Physics at Chalmers, and also the co-director of the Chalmers Nano Area of Advance. And since many years, I have been acting as scientific advisor to Insplorion AB. Now, in fact, the history of these plasmonic hydrogen sensors that I will present you today goes back all the way to my PhD. And this is where I would like to start this story because it is quite interesting. It actually started with a mistake back in 2005. I was a fresh graduate student at Chalmers in the group of Ben Cosimo, and I was tasked to develop the nanofabrication of platinum nanoparticles and study their optical properties. And this is what I did, and I made my samples. I was very happy about my results, but I had a colleague in the office next door who was working with fuel cells, intending to use platinum, the same metal, as a catalyst for the reactions in the fuel cell. But a few or half a year before her PhD was due, all her experiments stopped working. The fuel cells didn't work. And she was pretty desperate and first trying to find the mistakes that she could have made herself. Ruling all this out, in the end, the only thing remained was that, well, the catalyst that she was working with maybe is not platinum. So they investigated this, and indeed, someone, we still don't know who, exchanged the evaporation sources in the machine we used to make these samples from platinum to palladium. And at the bulk level, you cannot really tell the difference. They look the same, they look metallic. Now, while for her, this was a big problem, for me, it meant that I already had made a large batch of samples, not only with platinum nanoparticles, but also with palladium nanoparticles, because optically, I couldn't see a difference, so I didn't even notice. This is the reason why my first publication is entitled Plasmonic Properties of Supported Platinum and Palladium Nanostructures, so this was very convenient, but it is actually also the reason why a few years later I was able to publish a work which is essentially the foundation of Insplorion's plasmonic hydrogen sensors of today, where we used these palladium nanoparticles that I, by accident, had made to investigate hydrogen absorption in these nanoparticles by means of light. Now, what makes this possible, and what is the other foundation of a plasmonic hydrogen sensor, is the fact that many metals absorb hydrogen gas like a sponge, and they form, when they do that, a new material, you can say, which is called a hydride. And in this little sketch that we have in front of us here, this process is depicted, and you can see that in each circle, the mesh should kind of illustrate the atomic lattice of a metal. And then the black dots here constitute a hydrogen atom that is localized between the atoms of the metal, so in an interstitial lattice position. And the number of hydrogen atoms that is sitting on this interstitial lattice position depends on the pressure or the concentration of hydrogen around the metal. So at low hydrogen pressures, we will have few hydrogen atoms dispersed in the metal, and at very high hydrogen pressures, we will have essentially all the interstitial lattice positions filled with hydrogen. So in this way, the loading of hydrogen in these metals depends on the hydrogen concentration. The metal which has been most studied in this respect, because it absorbs and desorbs hydrogen in this matter and forms a hydride at ambient conditions, temperature, and pressures, is palladium. And when palladium absorbs hydrogen, well, you can imagine lots of hydrogen atoms have to find space inside this system. So it will expand its volume quite dramatically. It will become larger. And since each hydrogen atom also brings along an electron, we will also change the electronic and therefore the optical properties of the system as it absorbs hydrogen. And this is very nicely illustrated on this next picture that soon will be turned into a video, where you see a flower reflected in a thin film of a magnesium titanium alloy, a mixture of these two metals. And since it's a metal, it is highly reflective. But as we expose this to hydrogen, you can see that the reflection of the flower almost disappears, and that is because hydrogen has been absorbed into this thin film. It has formed a magnesium titanium hydride, which is no longer a metal, but actually an insulator, and therefore does no longer efficiently reflect light. And it is this optical contrast between a metallic state and the metal that has absorbed hydrogen, which is the basis for optical hydrogen sensors in general and for plasmonic hydrogen sensors in particular. Now, going back to my very first scientific publication from 2007, this is what we demonstrated. We demonstrated that one is able to measure hydrogen and a change in hydrogen concentration using nanoplasmonic sensing. We put palladium nanoparticles on the surface, as you can see in these images to your left, put them into a measurement chamber through which we shone light, whose intensity we measured with a spectrometer. And the inside of this chamber, we could expose to hydrogen gas and vary the pressure in a controlled way. So as you see here, if we plot the amount of light through this chamber peak, where the palladium nanoparticles strongly interact with the light, absorb part of the light, and as we then increase the hydrogen pressure from nothing, red, to 150 torr, you can see that this peak feature changes both its position along the wavelength axis, but also its general appearance, and therefore manifests the fact that hydrogen has been absorbed into these palladium particles because we have changed the hydrogen concentration around them. If we do this systematically and extract the position of the maximum of this peak along the wavelength axis and plot this as a function of applied hydrogen pressure, we get this optical so-called isotherm, which has this name because it was measured at a constant temperature, where we can see that this peak shifts a little bit as we increase the hydrogen pressure up to a certain point where it shifts a lot. So we have a large optical contrast, and that is when this hydride, this new material, is formed. And when we reverse the process and decrease the hydrogen pressure and follow the blue symbols, we see that this process is reversible and that the optical signal essentially returns to the same point when we have eliminated hydrogen from our measurement chamber. And in most simple terms, this is a manifestation of the optical hydrogen detection capability of plasmonic palladium nanoparticles. Now, if we look at the bibliometry, that is, what has in the scientific community been published since 2007, when I published my seminal paper here, when we just search for the keywords plasmonic and hydrogen and sensors, you see that up to 2022, 238 publications have been recorded in this database, about 7,300 citations. So this is a lot, and you can also see the development. The first few papers here were my own, and then this field has accelerated quite rapidly, which shows two things. First, it is not only something that I have come up with and that I do in my research group at Chalmers, but of course, many groups across the globe have caught interest and are working with these kind of sensors. And it also shows that the idea, the fundamental concept, is genuinely interesting and relevant to pursue, and that it by now stands on quite solid scientific grounds. Now, why is that? Why are these plasmonic and thereby optical hydrogen sensors so interesting? Well, it is because, as you know, they change the optical properties during hydrogen absorption. But they do that without the need for any electronics. So you can just simply read off your signal by a light beam, which makes them intrinsically safe. There is no risk that you generate a spark somewhere which could ignite a hydrogen air mixture. And secondly, they are hydride based, which means they are based on this process where a metal absorbs hydrogen, and only hydrogen, no other molecules, like a sponge, which means it makes them very selective. They do not react to other molecules that might be in their surrounding environment. They only react this strongly towards hydrogen. And as you also have seen, the optical contrast can be huge. We go from a reflective mirror to a non-reflective insulating material. That large optical contrast can be translated into potential for very low limits of detection, which means we can potentially measure very small concentration changes of hydrogen, which is one criterion for an excellent hydrogen sensor. In principle, you can make such optical hydrogen sensors in two ways. You can rely on thin films, where you measure the transmittance of light through the film and how this is attenuated as a function of hydrogen concentration, or you can work with nanoparticles using the plasmonic effect that we do, which is essentially that you rely on the electric field of a light wave polarizing the particle, displacing the electrons and the atoms in the system, thereby giving rise to a very strong interaction with light, amplifying the interaction of the light with the particle and thereby also of the particle with the hydrogen. Now, focusing on nanoparticles, the simple most plasmonic optical hydrogen sensor that you can make is a surface on which you place palladium nanoparticles. You have a light source, you shine light through that surface, and you analyze the intensity of the light that is transmitted on the other side. And as I've shown you already on the data of my initial publication, what happens when we do this, if we expose palladium nanoparticles to hydrogen, this spectral feature, the plasmon resonance peak, shifts, and it shifts reversibly, and at room temperature, it does it spontaneously as we change the hydrogen partial pressure. While this is, of course, nice from an academic perspective for a first proof of principle, from a practical application, palladium-based sensors are not very interesting because they respond very slowly. But for safety sensors that should detect hydrogen leaks to prevent explosions, they have to respond very fast. Purely palladium-based sensors also get easily deactivated by other molecules that we have in air all around us, such as carbon monoxide or water or sulfuric species and more. And we also have another problem. That is that the response of a palladium-based hydrogen sensor upon increasing hydrogen pressure and decreasing hydrogen pressure is different, because we need a higher pressure to form the hydride and a lower pressure to decompose it again. So we have this gap here, which is called hysteresis, which means that in this regime, whether the sensor shows a large optical response or a small optical response will depend on its history. And that is, of course, unacceptable for an online sensor application. There, what you want is a continuous, reversible, linear response of your sensor to a change in hydrogen concentration. So, if you wish, since the initial work that I did as a PhD student until today, where I've had several generations of my own students in my research group at Chalmers, what we have done is to amend these issues, the shortcomings of pure palladium. And to do that, we have taken guidance of the hydrogen sensor performance targets defined by the US Department of Energy, both for stationary and automotive hydrogen safety sensors. And we have quite systematically tried to address the most urgent issues, such as, for instance, to reduce the detection limit, to reduce the response and recovery time, to increase the accuracy, to be able to operate the sensors in challenging chemical environments, such as humidity and also others. And our approach has been, as scientists, of course, not only just by trial and error to try to improve this, but to always understand the underlying limiting factors, such that we, based on that understanding, rationally could design a better version of a material, for instance, that we would use for these sensor applications. Now, since 2007, from my group's perspective, this has resulted in a quite significant research output, a total of 33 publications, whereof multiple in quite high impact and well-renowned Nature family journals, which has made me and my group become key opinion leaders in the field where we drive this development because we understand these systems. And if you want to translate these 33 papers into research funding, it's research projects worth roughly 75 million Swedish crowns. That has brought us to from where we have been in 2007 to where we are today. In other words, I think it's fair to say that the plasmonic hydrogen sensing technology stands on very solid scientific ground and is based on a quite substantial and deep understanding of these systems and what limits them and how we can improve their performance. Now, for the rest of this presentation, I will share with you some examples of milestones, development milestones that we've had over the years in order to bring nanoplasmonic hydrogen sensors to the level they are today and that Insplorion are bringing to the market. So the first key step was to get away from pure palladium. And it is known that mixing metals, making alloys, is a way to improve the hydrogen absorption properties of metallic systems. So we developed a nanofabrication protocol that allows us to make surfaces decorated with well-defined metal nanoparticles comprised of multiple elements. In this example here, it's a mixture of 33% gold, 33% silver, and 33% palladium. And as you see in these EDS images, the elements are beautifully and evenly distributed across the particles, which confirms that we really have formed a homogeneous alloy where these three elements are mixed at the atomic level. Now, why these elements? Well, because it turns out if you mix palladium with 30% gold, you eliminate this hysteresis, this region where the sensor response would not be well defined, and you obtain an essentially linear response over multiple orders of hydrogen pressure, which is, of course, very beneficial for a sensor because now each optical signal position will correspond to one single hydrogen pressure in the surrounding of the sensor. Forming alloys, it turned out, has other beneficial aspects. For instance, if we make a ternary alloy where we mix not only palladium and gold, but also add 10% copper to the system, we form a surface that does no longer bind other species like carbon monoxide strongly to the surface, which means that in contrast to a pure palladium sensor that would be completely deactivated in the presence of carbon monoxide because the carbon monoxide molecules bind so strongly to the palladium that they don't allow hydrogen molecules to be absorbed. But if we add 10% copper, we can change that scenario such that the sensor essentially doesn't feel the presence of carbon monoxide. So if you look at this graph here where we have hydrogen pulses as a function of time and then read out the optical response of the sensor as a function of time, whether we are in pure hydrogen or in a 500 parts per million carbon monoxide background, the sensor response is essentially unchanged, as also seen here when we really zoom in on 3 pulses taken in pure hydrogen in the presence of carbon monoxide and then again without carbon monoxide present. So in this way, we have been able to show that we not only can get rid of this hysteresis, but also build sensors which can actually function in otherwise chemically deactivating environments. Following a similar or motivated by a similar problem, but following a very different line of thought, we also worked with a concept of using thin polymer layers on top of our nanoparticles as molecular filters, with the idea that hydrogen is the smallest molecule in the universe, and all other molecules that are around that potentially could influence our sensor or be activated are larger if we find the right polymer that has just very, very, very small pores. Only hydrogen can get through and therefore reach the surface of our plasmonic sensing particles, form the hydride and give rise to a signal, whereas all other larger molecules simply would not make it there, and thereby the polymer film would effectively protect our sensor surface. Here is an example where we have applied a coating of Teflon and plexiglass, if you wish, where you see that if we operate our sensor in 4 different environments, synthetic air means we have oxygen there, and either carbon dioxide, methane as a mimic for natural gas, carbon monoxide, or nitrogen dioxide. And then we apply 4% hydrogen pulses that, whether these background gases were there or not, the sensor response was essentially identical, proving that these polymer coatings indeed were efficient molecular filters and again enabled these sensors to operate in these chemically more demanding environments. Now, addressing another important metric of a sensor is limit of detection, which is important on one hand because, of course, in some applications you want to be able to distinguish very small changes in hydrogen concentration, but also if you think of a safety sensor where you want to trigger an alarm, the lower concentration of hydrogen that you can detect, the more time and the more safety margin you will have until you reach the critical concentration of 4% in air, at which hydrogen air mixtures actually become flammable. And again, also in part enabled by these polymer coatings, you can see here that we can resolve very small hydrogen pressure changes, the level of a few microbar, which translates into a few parts per million of hydrogen in air, which is orders of magnitude below the flammability limit. Yet another very important metric, which has been very, very difficult to improve, it's the US DOE's sub 1 second response time target, meaning that a safety sensor has to be able to respond to a change in hydrogen concentration of 1 millibar in less than 1 second at room temperature. To make a long story short, after a lot of work and thinking by carefully designing the size of our nanoparticles and selecting an appropriate coating, we were able to, as the first in the world, showcase a hydrogen sensor which would meet this target. Less than 1 second to 1 millibar hydrogen pressure at room temperature, which we then quite confidently could advertise as having made the world's fastest hydrogen sensor, which caught a lot of interest, of course, you can imagine, since this was a true milestone in the field. As the last point, I also want to mention that we cannot only deploy this plasmonic hydrogen sensor technology on flat surfaces decorated with nanoparticles that I've shown you before, but we have also demonstrated that one equally well can use optical fibers onto which you deposit these nanoparticles. In this case, it was again also a palladium gold alloy in order to get rid of this hysteresis effect. And as you see here, we can detect changes in hydrogen concentration, for instance, in synthetic air over quite long periods of time in a very reproducible manner. So this is a short overview of the state of the art and the history of the development, how it all started. When I now look forward on this last slide and sketch some of the opportunities that I see, it is that, of course, for us as researchers, it is to continue to demonstrate what is possible by pushing limits and by testing new concepts to inspire others and to further fuel this development of this very promising sensor platform. And we will, of course, keep doing that. Since, in my opinion, this technology stands on a very solid scientific and technological ground, it has a lot of potential. that we can explore moving forward. And in my opinion, this indicates that there should be a place for this technology on the market. Future possibilities that we specifically explore currently at Chalmers are the use of machine learning techniques for the treatment of the data these sensors generate to improve multiple aspects of the performance. The concept of multiplexing, that is to combine different materials, for instance, different types of alloys, which all have their specific advantage in a certain environment, but work less ideally in another environment. But by combining them, the idea is that we can make more robust sensors that can operate in complex environments. And we will, of course, continue to explore completely new types of materials and coatings to further advance the nanoplasmonic hydrogen sensing technology. Thank you very much. I hope you found that interesting, and I wish you a good rest of the day.